Yes, thank you so much. Let me get my slides up.
Anh vào lại rồi. Tại vì
So I think you can see my slides, right?
Yes. Yeah.
Okay, good. Okay, so well, I want to first thank Joshi and Fumia for inviting me for this talk. It's yeah, thank you so much. I will tell a little bit about my research into designed intelligence of in soft medical robots. So I am a assistant professor at the TU Delft in the Netherlands, and I mainly focus on the development of medical devices such as catheters, and I mainly develop like steerable catheters or other medical devices. If you look into current surgical robotic, you see that they're often quite bulky with very little degrees of freedom, and they often have limited or no force feedback. This makes that these devices are often very difficult to control, and also like when you have narrow cavities such as in the brain or a very dynamic environment such as in the heart, it's very difficult to control these devices, and this makes them often very unsafe. So what I want to do is actually look more into the development of more soft and flexible instruments and robots for use during surgery by integrating also this embodied intelligence to improve the effectiveness, to make them being able to go deeper inside the human body, but also to make them safer. So, of course, you're all quite aware of these different types of intelligence that there are. So we have different layers of intelligence, such as artificial intelligence, morphological intelligence, and, for example, physical intelligence. If you look at like medical robots, you often see that they use artificial intelligence. So it's more about having this rigid robot that's controlled by a brain, but the segments are rigid and the joints are position controlled. If you look a little bit further in these structures, then you see that because of this, they have this low dexterity and these safety risks, and they're also relatively slow devices. So if you look further and deeper and look more towards like morphological intelligence, in which you, of course, like part of the computational load is offloaded off the brain and more of the morphology is used for the interaction with the environment, then you get devices such as catheters and guide wires, which are more flexible, they're more soft and under-actuated, and therefore they have these richer dynamics and can adapt better to the environment. However, what we see is that they're still limited in what they can do, similar to what my previous the talk said, is that they can't really adapt to all the shapes that you can be found in the body, and they're sort of a general solution for everything. But what we want to achieve is that we can control the properties of the catheters or the guide wires to improve this. So what we do is we look a little bit into how an octopus moves. Of course, the octopus is a very well-known example of a soft animal, and it uses this very interesting way of reaching for fish in like a bending motion. And when it reaches the fish, it makes a type of articulated structure similar to how an elbow and an arm works. So that's very interesting because even though the structure is fully soft, it still uses a type of rigid structure to move. So that's a little bit part of the research that we're focusing on in creating this similar type of movements in catheters so that we can, for example, reach and extend, but also once we reach that we can make an articulated structure with joints at specific spots, which of course makes for higher adaptability to the dynamic environments inside the body. So what we looked at a little bit together with Professor Endo and Suzumori from Tokyo Institute of Technology is using, for example, smart McKibben actuators for this to create this tentacle. In here, we're exploring how to make these McKibben actuators smarter to create this kind of reaching motion and also create these joints. So I can't tell much more about it now, but soon there will be more about this. Next, we also look into the octopus ability to actually grab fish. So if you look at an octopus, of course, the tentacle have a lot of different like suction cups, of course, to grab fish or rock. And this is very interesting because if we look at the man-made suction cups, we can't easily do this with like rocks or something that's quite rough. So we were inspired by this and we created this suction cup, which you can see here, which is inspired by the suction cup of the octopus. And we use this to grip tissues. And here you can see a little bit how it looks. So we looked into how does the octopus create this seal on these different substrates. And we found that by creating this kind of structure using flexible materials such as silicone combined with meshes, we could create a similar type of compliance to be able to lift different types of tissues. And here you can see the suction cup with gripping different materials such as an egg or a banana, but also in the bottom a video of the suction cup lifting a little chicken heart. And you can see it can also pick up objects that are smaller than itself, so bigger and smaller. So we tested on different types of tissue and it worked quite well as well. And then we were thinking, how can we improve this cup? So we actually were in contact with people from AMOF in the Netherlands, particularly Bas van Overvelde. He's an associate professor there. And we thought, how can we make this smarter? Because what we want to do actually is if we grab tissue, we want to be able to sense how stiff the tissue is and how far it's sucked into the suction cup. One, that's for safety, because we don't want to apply too high of a vacuum on the tissue to prevent damage. And two, it's also we can say something about the tissue that we're gripping. So is it healthy tissue or is it, for example, tumorous tissue? So what we did was with them is that we looked into we didn't add a sensor, but what we did was we looked into the vacuum pressure inside the cup, and we were able to determine based on the deformation of the cup itself and also the pressure inside the cup what the stiffness was of the tissue that we were gripping. So this is of course very interesting for us, and we're currently now looking further into like actually looking for if we can detect tumors, for example, inside the body with this technique. Finally, I quickly want to show you one last project that we're working on, which is a catheter that can actually alter their frictional properties using ultrasonic vibrations. You can see the rings here that are vibrating. And what we actually want to do is that once you insert a catheter in the blood vessel wall, you can still have a lot of damage because of the sliding motion. But once you reach the heart, actually you want to stay in place. So then you want to have an anchor. So what we can do with this technique is actually create this by changing the frictional properties. So what we do is we put a vibration on it, and then we pressurize the air in between the two surfaces, which causes either levitation or attraction. And we performed an analytical study, and we found that we can achieve this levitation of about 30 microns in a liquid environment. So that allowed us to change the frictional properties. So with this, we can then safely anchor ourselves, but also levitate during navigation using these rings. And my PhD student, Mustafa Atalla, he tested this technique on a pig aorta. And here you can see one of the rings sliding over a piece of pig aorta. And we measured the frictional properties during this experiment. And as you can see here, we found that we were able to reduce the friction between 20 to 40%. So that's significant for us so that we can more safely move. And in the end, of course, we want to create like not just one ring, but the whole catheter structure. So that's what we're currently working on right now. And then, of course, I hope with these techniques that we can decrease the number of complications and make procedures more efficient, and also decrease the workload of surgeons because we have an aging population, and that's very important for the future. So thank you very much. And yeah, I'll be here for the panel discussion as well.
Thank you, Aimee, for great talk. It's very nice to learn that how your soft robot ideas can be utilized in a practical use. Thank you very much. Okay, then